Okay, we can get started. We're going to continue today's lecture discussing distortion. Before we start the lecture, I wanted to make a couple of brief announcements. First of all, as you all know, the new homework is posted online. Hopefully that's not news to you. The other announcement is that the solutions for number 2 are up. We've been a little bit slow in getting the solutions up. This one I think we got up over the weekend. But we're going to work hard to make sure the solutions are up the day that the homework is due. So that's good for you because you get more time to look at the solutions before you start the new homework. It's also bad news, which means I can't accept late homework. So take that into consideration when the solutions go up, your solutions are invalid. You can't turn them in. Any questions or comments before we start? All right. So last lecture we started looking at distortion. Last couple of lectures we looked at nonlinear systems. And in particular I want to spend a little more time talking about gain compression. Now the idea of gain compression is very simple. If you go out into the lab, in fact I encourage you guys to do this, take a commercial amplifier and plot the power gain. Well, first plot the output voltage as a function of the input voltage as you vary the input. So this is the input, this is the output. And this could be an AC signal, it could be a low frequency signal, but the idea is that what you'll find, as we discussed last lecture, is that this output will eventually compress. And likewise in the negative direction it may do something similar. And so the apparent gain, the gain is proportional to the slope, reduces. Now you can also have expansion, less common, but gain expansion means that actually this thing might look like that. So the slope increases at high level inputs. Now even though you might observe this for small inputs, eventually if the input gets large enough you will experience expansion, compression. Because most systems eventually will compress, let's say at VDD, the power supply voltage. So if we look at the gain, the apparent gain as a function of the input, let's say this is the input signal, and let's say this is the output signal over the input, we'll call this the apparent gain. Then at low frequency this will be very constant, but we claim that at high frequency it'll basically fall. So if we take data points like this, if we look at the input-output relationship from here and just plot it, we find that the gain drops. So this is called gain compression. Yes?
You say high frequency, you mean high amplitude?
Okay, thank you. High amplitude, yeah. Yeah, sorry about that. So here we're talking about essentially putting in signals which are in the passband of the amplifier. So effectively, they're either low frequency signals or they're signals within the passband. So there's no frequency effects going on. This is just due to the nonlinearity of the amplifier. Okay. Now what's interesting is if you find the point at which the gain is dropped by 1 dB, we call that the input 1 dB compression point. P input minus 1 dB. And likewise on the output, we could call this P out minus 1 dB. And this is a very useful number. If somebody tells you I have 2 amplifiers and one compresses 1 dB compression point is 5 dBm and the other one is 0 dBm and you need lots of power, obviously you would choose the one that has higher compression point. Now the reason that we don't like to operate an amplifier beyond compression will become very clear in this lecture. So it might seem, sure, just use an amplifier out here, you're going to get less gain, but it's still a good amplifier, right? No. We'll see today why we don't want to use an amplifier in this region. So well below 1 dB compression point, that's the small signal region where we like to operate an amplifier. Okay. Questions or comments? All right. It really depends on the standard of communication that you're using. So if you're using let's say a modulation scheme that has constant envelope, then you could go all the way up close to compression if it's just a single tone. This question, there isn't a simple answer. It really depends, right? And we'll see various flavors of depends in today's lecture. Okay, that's a good point. All right, so let's look at let's calculate the apparent gain based on the small signal analysis that we did. So remember, we assume that we can do a Taylor series expansion on the nonlinearity, and let's say that the cubic term is sufficient to understand the behavior of the system. So remember, if we put an input amplitude, let's say S1 cosine omega 1t, and we look at the cubic term, if I take S1 cubed cosine cubed omega 1t, I can never remember these, so I just do it from scratch. I can write this as S1 squared cosine omega 1t. Cosine squared I do remember. That's 1 plus cosine 2 omega 1t divided by 2. And now if I multiply this all out, I get S1 cubed 1/2 cosine omega 1t plus, I can write this as 1/2 divided by 2 multiplied by 2 cosine omega 1t cosine 2 omega 1t. And I know that 2 cosine alpha 2 cosine beta is cosine alpha plus beta plus cosine alpha minus beta. So let me write that out. So I get 2 over 4. The sum frequency is cosine 3 omega 1t, and the difference frequency is cosine omega 1t. Okay? And it's really this difference frequency that's very important, because this is at the fundamental. And so we see that the cubic operation generates two fundamental signals, and depending on the sign of A3 in this expansion, these fundamental tones could either add to the linear gain term or they could subtract. And so for a compressive nonlinearity, they do subtract. So let's collect these terms. So I could say that my output signal at frequency omega 1 is equal to A1 times the input amplitude, which we're calling S1. And now I have two more amplitudes here. I have 1/2 A3 S1 cubed plus 2/4 S1 cubed A3, which is the second term here. And if I divide that by the input at omega 1, that's my gain. Well, that's simply S1. So my apparent gain is A1 plus these terms just add, so 3/4 A3 S1 squared. And I can factor out A1. Let's go back here. So it's 1/2. This is 1/4. Let me see what I did wrong here. This 2 shouldn't be there. That should be 1/4. That makes sense now. Okay, just a small mistake. So this is 1 plus 3/4 A3 over A1 S1 squared. So now we see that the gain is a function of S1. And if A3 over A1 is less than 0, which is 0, then we have compression. Okay. Now from our general discussion, we know that any odd power will generate fundamental, right? But we're assuming here that the third order is going to dominate. That's going to be the largest term in the expansion. Any questions about that? Okay, so what we can do now is find when this gain reduces by 1 dB. So when this term here is equal to minus 1 dB, in other words, when 20 log 1 plus 3/4 A3 over A1 S squared is equal to minus 1 dB, that corresponds to the input amplitude, which we called P minus 1 dB, P input minus 1 dB. Okay, so let me solve that. That's really easy. If you have a calculator handy, you can verify that I need this term here to be roughly 0.11, then this thing corresponds to minus 1 dB. And if I solve for that amplitude, I get 4/3 A1 over A3 square root times square root of 0.11. Okay. Now this term here is going to play a very important role. In fact, I should have introduced it first. What we'll see is this term is called the IM3 intercept point. What does that mean? So let me discuss the concept of an intercept point first. But for now, you can see that this is just a simple equation. It tells you that if the input amplitude gets this large, then the gain should have dropped by 1 dB. Okay? Any questions about that? Is that pretty clear? All right, let me discuss the concept of compression point, intercept point. It's a very simple concept. It's a graphical way of looking at intermodulation distortion. So let me basically plot on a log-log scale. So log of V in, log of V out. And since we're on a log scale, input voltages correspond to powers as well. So this could be 20 log, 20 log. So this represents the input power, this represents the output power. Now, if I plot on this log-log scale the input-output relationship, I will get a curve, right? And because eventually there's gain compression, I know that if the input is sufficiently large, it'll start deviating from a straight line. But for now, let's focus on this straight line. So this is the output, or the fundamental, appearing at my amplifier. So very simple. I put in my input, and I have my output at omega 1. I have my output at 2 omega 1, my output at 3 omega 1. If I add two tones, so if I have omega 1 and omega 2, I know that I also generate IM2 and IM3 products, right? So last lecture we found that IM2 products are frequencies where we have omega 1 minus omega 2 and omega 1 plus omega 2. IM3 products are frequencies like 2 omega 1 minus omega 2 or 2 omega 2 minus omega 1. So what I'm going to look at is the power, so plot power of intermodulation products. In particular, let me look at the power. Let's say I go out here and I measure that at a certain input power, my IM2 is down by this much, right? So ratios, IM2 is a ratio between the intermod component and the fundamental component. On a log scale, it's just this difference. Let's say that I find that, let's just say arbitrarily, this is 40 dB. That at a certain input power level, my intermod power is 40 dB down from the fundamental. Well, how does it vary with input? If I vary my input, what happens to this intermodulation component? Well, if we're talking about IM2, we know that IM2 is proportional to the square of the input power, right? So if I were to plot this on the same plot here, if this slope were 1, this slope would be 2. So I find that my intermodulation term grows faster than my input. And eventually, if I make my power large enough, these 2 points will intersect. I call this point of intersection my IP2 point, intercept point for second order intermodulation. And I call the input power where this occurs input IP2, and I call the output power output IP2. Okay? So this is just a graphical interpretation of what's going on. What's interesting is that as I change, let's say, my input power by, let's say this, for instance, corresponds to minus 50 dB input power. Let's say I go to minus 40 dBm. Say it's on a dBm scale. Well, that means that my intercept, my IM2, changes by also 10 dB. So if I change the input power by 10 dB, the intercept point will also change by 10 dB. So here, instead of 40 dB, it'll be 30 dB. And so if you know the IM2 at any given point, it's very easy to calculate how far you need to go to get to the intercept. If I'm at 40 dB here, right, 40 dB difference, I just move 40 dB forward, and boom, I have the intercept point, right? Now, the reason that intercept point is so popular is that if I know the intercept point for the amplifier, it's kind of a universal number. I can now predict the distortion at any given input power level. So I just need to specify one number, IP2, let's say input IP2, and then you, as the user of this amplifier, can figure out how much distortion you're going to get for any input power level. If your particular application needs 100 dB of IM2, then you've got to back off 100 dB from the IP2 point. Okay? So it's basically no new concepts here. It's just a graphical way of looking at IM2. Okay? Any questions about this? Well, we have an equation for IM2, right? So last lecture, we found that the IM2, can you guys help me if you have the lecture notes? Is it A2 over A1 S input squared? Okay, I have it here. Yeah, it's actually proportional to S input, not S input squared. Yeah. So if this is the IM2, I can just set it equal to 1 and solve. So S input equals to A1 over A2 is my P IP2 point, input IP2 point. I set it equal to 1 because when it's at this point here, at the intercept point, IM in dB is 0 dB. That means your distortion is equal to your signal level. That corresponds to an IM of 1. Now let me just point out that you would never actually operate your amplifier here, right? For a couple of reasons. First of all, if your distortion were really equal to your input signal, that's a pretty bad situation to be in, right? Especially if you can't filter out these distortion products. So for the first part, you don't want to operate here because the distortion is so large that you can't distinguish your signal from the distortion. The other interesting point is that this is really an extrapolated point, right? So we call this the extrapolated intercept point because in reality these curves are not straight as you make the signal larger and larger. They're only straight for very small signals. So this point here is not the actual intercept point, it's the extrapolated intercept point. What's cool is I can do a measurement at really low power. I just need a couple of points here, and I can extrapolate the IP2 point. In fact, it's even better than that. If I go to really low powers, then I know these slopes ideally should be 2 to 1 and 1 to 1. So from just one point of IM measurements, I can extrapolate the IP2 point for an amplifier. Questions? All right. So this is a way to calculate directly from power series. Alternative is to do it graphically. And this is the way we do it with measurements. We typically will measure the IM at several input points, basically verify that the amplifier actually fits within these lines. We do that just to make sure we're not crazy. You know, maybe the amplifier is hooked up incorrectly, make sure the slope is right, and then you extrapolate to get your IP2 point. Okay? Well, a very similar concept is your third order IP point. And in fact, it's a more important concept for many systems, for most systems. Remember last lecture we talked about second order intermodulation falls at low frequency and at roughly twice the frequency if you have two tones, right? So if you have tone omega 1 and omega 2, then we had an omega 1 plus omega 2. That was an IM2 term, so this is a IM2 product. And then we have another term, which is also an IM2 product at frequency omega 1 minus omega 2. Okay. These are pretty disparate frequencies. I could filter out, if I have a narrowband system, I could put a filter here and get rid of these tones. But IM3, as we discovered, falls very close. So my IM3 tones are at frequencies 2 omega 2 minus omega 1 and 2 omega 1 minus omega 2. So recall that I can't easily filter out these tones. You could say, well, you can make your filter sharper, but I can move these tones closer together, right? So in fact, I never really send tones, I always send modulation. So there's always going to be lots of tones close together that will produce this kind of distortion. So IM3 is particularly nasty because we cannot filter it out. Now if I do the same thing that I did graphically, I can again make a plot of my fundamental output. This is VO omega 1. And then I can make a plot of V, let's say 2 omega 2 minus omega 1. This is the amplitude of the third order. And now you'll notice that if the slope here is 1 to 1, the slope here is going to be 3 to 1. That's because we know intermodulation goes like the cube of the signal. So this IM tone catches up very quickly because it's moving 3 times as fast on a log scale. And again, I can define the intercept point. And I call this my input IP3 point, and this point my output IP3 point. And again, IP3 is the way you typically specify. If you go look at a data sheet for an amplifier, they're not going to tell you what IM3 is at some power level. What they will tell you is the IP3 point. And from the IP3 point, you can calculate basically where you can operate your amplifier. You know, how much distortion can you tolerate? Well, if you can, let's say the IP3 point arbitrarily is at 0 dBm. Let's say you need 100 dB of IM3. What input power, what's the maximum input power that you can put in? Anybody? So if this is the IM3 at a given input power, if I move over 10 dB, how much does the IM3 decrease? By twice, right? So 20 dB. So if I want 100 dB IM3, I have to back off 50 dB from the IP3 point. So operating at minus 50 dBm would give me over 100 dB or 100 dB theoretically of IM3. Okay? Questions? Comments? All right, so what we're going to find today is, yes, there's a question.
IM3 is 3 by 4 SI squared. So where did the cube term come from? So why is it cube? Am I missing something?
Let me actually solve the equations and we can see where that comes from. Okay? See what? Okay, let me answer your question. It's actually quite simple. Look, IM3 is increasing like the square. but the intermodulation is increasing by the cube. Does that make sense?
Yeah.
Okay. Good question. Very good question. All right. Let me shoot ahead here and nope, that's not it. All right, so let me again go back to last lecture and just set IM3 equal to 1. So that's 3/4 A3 over A1 S input squared, right? Let me verify this. Yeah, that's right. Okay. So now let me just solve for S input to get IM3 of 1. That gives me 4/3 A1 over A3, let's say magnitude, square root. So this is the input IP3 point calculated directly. Usually we measure it. So the usual way of calculating it and we use the same graphical approach that we discussed before. But what's interesting, what I want to point out to you guys, is this term in the square root. 4/3 A1 over A3. Let me go back a few slides. Look at the input that I need. What is this input power? This is the input power that corresponds to the gain dropping by 1 dB. It's also 4/3 A1 over A3 square root. And that's why here I wrote down this is the IM3 intercept point. Okay? So at that point I hadn't introduced it. Didn't want to confuse you guys, so let's go back and look at that. And so you can see that the input 1 dB compression point is related to the intercept point by this factor of square root of 0.11. I believe that's 9.6 dB. So if you have a calculator, you can verify this. But this corresponds to backing off about 10 dB from the intercept point. So if someone tells you, I have an amplifier, it has a plus 0 dBm intercept point, okay? And I want to operate it at the point where the gain is dropped by 1 dB. Then you know you back off 10 dB from that intercept point, and at that point the gain is dropped by 1 dB. Okay? So keep this number in mind because it's going to pop up over and over again in today's lecture. Okay. Questions or comments? If you find this discussion a little bit confusing, we're going a little bit fast, don't worry. Take your time, look at the notes, come to office hours, ask questions. It'll all come together. It's not so much that it's difficult, it's just we're introducing a lot of terminology. All right. Let me now finally introduce one more term, and this is the concept of an out-of-band blocker. So the idea is following. Let's say I have an amplifier. Could be a radio amplifier, for instance. And unfortunately, no matter what you do, it's going to have some nonlinearity. And what I'm concerned about is, what if I pick up two signals here? I have, let's say, on a spectrum diagram, I have the strong signal, which is the unwanted signal. And then this tiny signal here is the wanted signal. Okay? So the question is, can I put this through an amplifier and hope that this unwanted signal doesn't mess things up? Okay? And what we'll see today is that, in fact, no. If you have nonlinearity, what you do is you get jamming. The concept of jamming is that this big tone reduces the gain of this amplifier so that the small tone sees less gain. In fact, what we'll do is we'll calculate when the apparent gain of this amplifier is dropped by 3 dB. And we'll find that power level, we'll call that power level the basically out-of-band blocker power level, 3 dB out-of-band blocker power level. But forget the terminology. It's more important to figure out the concept here. This is a really bad situation because we don't really have control over what comes into our amplifier, right? If you're in a laboratory and you're doing a very careful experiment, you're very delicate, you buy triax cables, you hook everything up, you do shielding, and so you only pick up, let's say, your measurement data. That's fine. But what if you're out in the real world? If you just stick an antenna out, there's no way you can control what people are transmitting into space. So you're going to pick up everything, all the junk. And it's very likely that some of the junk that you're going to pick up is going to be stronger than your signal. Okay? So let's see how jamming works. All right, so again, I'm going to make the assumption that I have a memoryless nonlinearity, and let's say I can use a power series to describe it. Okay? And now on my input, I'm going to assume I just have two signals. A huge blocker signal and a tiny desired signal. So this is the wanted signal, and this is my blocker. Now keep in mind, this guy can be much, much larger than this guy. So for instance, this wanted signal might be minus 100 dBm. This blocker might be minus 60 dBm or minus 50 dBm. So 50 dBm, or 5 orders of magnitude more powerful than the signal you're trying to detect. Okay? All right. Well, if I now plug in, basically I know I'm going to get the blocker at the output. But let's say that's not an issue because I'm going to filter this out. Let's say I'm going to filter okay? This is the desired signal that comes through. And then I'm going to have basically square products. This is going to lead to IM2 tones, right? But again, let's assume I can filter out my IM2 tones. And then finally, I'm going to get this cubic term. And what I like to show you is that this cubic term generates all the nasty stuff. So let's expand out this cubic term. So let's focus on the cubic term. So the cubic term is A3 times this cubed. So this is going to give me S1 cubed cosine cubed omega 1t. It's going to give me S2 cubed cosine cubed omega 2t. It's going to give me 3 times this term squared times that term. So S1 squared S2 cosine omega 1t squared cosine omega 2t. It's also going to give me 3s2 squared s1 cosine omega 1t cosine squared omega 2t, and so on. Okay, so I'll stop there because these are the important terms. Now if I look at this first term here, I know that this is going to generate omega 1 and 3 omega 1, right? That's okay. This is not at the fundamental frequency that I'm worried about. Again, maybe I can filter these out. What I'm really concerned about is energy being generated at omega 2. Okay? Likewise, if I look at this term here, I'm going to get omega 2. The omega 2 term will, of course, change the apparent gain. That's what we studied in gain compression. And it also will generate 3 omega 2. So that'll be my third harmonic. All right? Look at this term here. This term is the nasty term. Why is it nasty? Well, remember, S1 is a big number. S1 is that big signal, and I'm squaring it. So it's even bigger now. And here I have cosine squared, which produces a DC term and a term. So this is going to have DC, and 2 omega 1. And when I multiply it out by this term, I'm going to get omega 2. So when I multiply this, I'm going to get omega 2, and I'm going to get intermodulations 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Okay? Well, this is the term that I care about. This is my fundamental. This is the wanted. So let me focus on this term. Now you may notice that I have a similar term here. I'm going to neglect this term. Why is that? It's much smaller, right? Because here I have S1 squared, here I have S2 squared. Remember, S1 is small. So this term is small in comparison to that term. Okay? Any questions about the setup of the problem? All right, so let's focus on that term. So let's say the blocker term looks like A3 times 3S1 squared S2. When I square cosine, I get 1/2, basically 1 plus cosine 2 omega, which we don't care about. So this all appears at cosine omega 2t. So now let me compare, so I can write that my output, so now I can write my apparent gain is equal to, let's say, A1 times S2, right? That's the linear term, plus this nonlinear term, which is A3, 3S1 squared S2, 3/2. And if I now divide this by the input, which is S2, the apparent gain looks like A1 plus A3. I can see that S2 cancels out of this equation. 3/2 S1 squared. And I could write this as A1, 1 plus 3/2 A3 over A1 S1 squared. Now if A3 over A1 is less than 0, so A3 over A1 is less than 0, which is usually the case for compressive nonlinearity, I can see that my blocker is reducing the gain, the apparent gain, experienced by that small signal. So the small signal doesn't know what's going on. It goes through the amplifier, and instead of experiencing a gain of A1, it experiences a reduced gain. And the amount of reduction depends on how strong the blocker is, right? Even if I have a really good filter at the output to get rid of all the intermodulation terms, right? Even if that were theoretically possible, I still will experience less gain. This is the concept of jamming, okay? Any questions about this? Yes?
So when we put an S and R, we do the signal in-band to the noise in-band, right? Obviously, this is that any out-of-band signal will be IM3 interference into in-band. So when we calculate noise, we have to integrate over the whole spectrum.
Okay. You brought up several concepts. Let's keep it simple, the discussion. Let's not talk about noise. Let's just talk about distortion. Now, true, there is intermodulation distortion that we already took care of that last lecture, right? You get intermodulation products. What we're seeing here is that even if you could filter out those intermodulation products, you're still going to experience less gain in your system. So this is not an intermodulation term. This is the term at omega 2, the desired frequency. So the gain of our system is apparently dropped because of this jammer.
Well, I guess my question is that basically we're susceptible to everything that's outside of our band.
That's true. And that's why it's so difficult to build radios, because you don't have a very well-defined spectrum. Now, of course, you can always filter, right? And that's the solution that people use. You put lots of filters at the input of your amplifier to try to filter out as much as possible jammers. But a filter can only do so much, right? A filter maybe gives you 20 dB of attenuation. Well, someone can turn up their power by 20 dB. Filters are also very bulky and expensive. So if we can eliminate filters by making our amplifier more linear, that's always a win. Okay. Now, just a few, give you guys a few applications of jammers. Of course, the military loves this concept, right? Because the military can now jam your communications. I heard a story once. This didn't happen to me personally, but somebody was down in San Diego near a Navy base, and they're trying to open the door of their car, and it just would not open. You know, they had a keyless entry system. Just kept trying it, and they thought, oh, the battery must be dead. You know, very frustrated. And then they just noticed that a big ship was going by at the same moment, a big tanker. Not a tanker, a big aircraft carrier was going by. And apparently, you know, it's standard practice by the military is a aircraft carrier or any kind of military hardware comes near the shore, they just turn on a huge jamming signal. Who knows? Maybe 10 megawatt. Who knows what power level they're using? But within a certain radius, let's say a radius where you could have a bomb in your hand or some kind of timing device, all electronics were inoperable. Certainly radios were completely jammed. A similar thing that you might use for military applications is you could try to jam someone's radar, right? If somebody is trying to figure out where you are and shoot a missile at you, you can send out a jamming signal, large signal, and try to jam out that interference. If it weren't illegal, jamming would be very convenient in places like restaurants and movie theaters, right? You can have a jamming signal, and so anyone trying to use their cell phone would get jammed. Unfortunately, it's illegal to do that. So, okay. I'm sorry. That's also another potential issue. If you have a pacemaker in your heart, it's susceptible to interference as well, microwave interference. All right. Okay. Let me see if I wanted to discuss. Oh yeah. So we should also finish this discussion up. You can see that this term here again has a very familiar format. It's proportional to some factor times A3 over A1. So let's find when this gain drops by minus 3 dB or by 3 dB. So let's solve for 20 log of 1 plus 3 halves A3 over A1 S1 squared. Let's make that basically minus 3 dB. And if I do that, I can find my blocking power, and you'll find that if you just do the math, it's equal to the minus 1 dB power plus 1.2 dB. Okay? So at this power level, the gain of your system will drop by 3 dB. Now remember at the beginning of class I said you don't want to operate your system where it gets very nonlinear. Well, this is one important reason why, because if you operate in this region, any kind of interference will completely jam your system and reduce your gain. You're much more susceptible to it here. Okay? Okay. All right. Any other questions? All right. So I think that's pretty much it for definitions. Al, does that cover it? What we skipped last lecture? Okay. Sorry, I was supposed to do this last lecture, but I got ahead of myself. All right, let me teach you guys a couple of other very simple tricks. First one is series inversion. And you might find yourself in a particular pickle where you can find your input signal as a power series of your output signal, right? Very easy to dream up situations where there's a nice clean function describing the input as a function of the output, but not vice versa. And let's say that analytically you can't invert the equation. It's some kind of implicit equation. Well, what you can do is you can take that implicit equation, do a power series for it, and then reverse the series or invert the series. So what we'd really like is a series that looks like this. What I can do is I can now just plug this in to this equation and make sure that the equation is satisfied. So I just say that S input is A1 times this whole expression plus A2 times this whole expression squared plus A3 times this whole expression cubed, right? And then I just need to make sure that the equation is satisfied. So let's equate linear terms. That's easy. If I equate linear terms, on the input I have 1, that's the coefficient. On the right-hand side, I have A1 times B1. And if I now look at this equation, there are no other linear terms. This is a squared term, this is a cubed term, and so on. Here, even the lowest power is squared, so the smallest term here is a square. Here, the smallest power is a cubed. So this is the only linear term, and quite obviously, B1 is 1 over A1. Okay? It's a very trivial result. Okay, now let's equate square terms. Well, there's no square terms on the left-hand side, right? Push this down a little bit. On the left-hand side, I have just S input. On the right-hand side, I have A1 times B2 S input squared, so that's one term I need. What other terms do I have? If I look here, I have a term which is A2 B1 squared. And if I search for other terms, I run out. Every other term generates cubic or higher. So I'm done. These are the only square terms. So now I can solve for B2. B2 is minus A2 B1 squared over A1. And B1, of course, is just 1 over A1 squared, so I have minus A2 over A1 cubed. Okay? And I can do the same thing for cubic terms. Again, there are no cubic terms on the left-hand side of this equation. This is the left-hand side here. The right-hand side, I have a cubic term which naturally comes out of here. So that's going to be A1 B3. Whoops. Okay. A1 B3 is a cubic term. If I look here, my A2 term will have basically 2 cubic terms. When I square this, I'll multiply this by this 2 times. So I get 2 times B1 B2 okay, and then finally I get a cubic term from here, A3 B1 cubed, and that's it. There are no other cubic terms being generated, right? Here everything is 4th order or higher. Here I'm getting 4th order or higher, and here likewise. So I'm done. So again, I solve this equation. I won't bore you guys with the math, but you'll find that B3 is 2A2 squared over A1 to the 5th minus A3 over A1 to the 4th. Okay? So this is a nice trick to have if you find yourself in a situation where you know the reverse of what you want to know. What's also really interesting about this equation is this term. What's interesting about this term? Well, what's interesting about this term is that, let's say our original relationship had A3 equal to 0. Okay? That means that in the inverse relationship there is no cubic term. When I invert that equation, though, boom, I can have a cubic term. So A2 interacts with A1 and produces a cubic term in the inverse. So just because the amplifier output to input relationship is, let's say, doesn't have cubic, doesn't mean that the inverse does not. Okay? So in particular, if you think of a square law device, if you apply an input voltage, the output current doesn't have any cubic, right? But what if you apply a current to the drain and look at the input voltage? Well, certainly that's the reverse. Certainly you can solve that analytically. You don't need to use this technique. But if the equations were more complicated, you would, and you would find that actually there is cubic term. All right. Any questions about that? Yes.
So what's an example where we actually know the input as a function of the output?
I just gave you guys an example. Let's say you had a transistor. Let's say this is my input current. So this is I input. And let's say this is my output, V out. Right? In this particular case, I know this, you could solve it analytically, okay? But you immediately know I output as a function of V in, right? Or I in as a function of V out. So one approach would be I would invert this and then do a Taylor series expansion of the inverse. Another option would be you directly Taylor series expand this equation and then invert it to get B1, B2, B3. Okay? Now in this particular example, again, I dreamed this up so it's very simple. Even in this example, if you include things like if I put a resistor here, that makes the problem more complicated, and inverting it becomes quite difficult, and you'll find that this is a useful technique. Okay. Any other questions about series inversion? Okay. Well, the other important trick is cascading, and this is actually a very practical situation. It's very common that you'll take, let's say, one amplifier and cascade it with another, right? So let's say that y is some nonlinear function of x, which again we Taylor series expand. And z is likewise, let's say, another function g of y, which we can call b1y plus b2y squared plus b3y cubed. What we're really interested in is z, let's say z1, c1 of x plus c2 of x squared plus c3x cubed. Okay? So if I cascade these two systems, and I know the individual Taylor series expansions, what's the overall Taylor series expansion? Okay, and that's actually quite simple. All I need to do is substitute this series for each y. Okay? And again, I can use the same trick as solving. I can basically equate this to this and solve for like terms. Okay? So let me do that. Let me do the linear case. So for the linear case, I have C1 on one side. On the other hand, up here I have B1 times A1. And I can see that B1 multiplying any of these other terms doesn't produce linear. Likewise, here I have y squared, so even my linear term gets squared, so I'm done. These are the only linear terms. And the result is quite obvious. The overall small signal gain is just the multiplication of the individual gains, right? You didn't need to do any math to do that result. What about the square terms? Now we need to do a little math. It's not so obvious. Well, on the left-hand side, I have C2. Now let me look on the right-hand side. On the right-hand side, certainly B1 times A2 generates a square term. Okay? You can see that that's it from this first equation. For my second term here, B2 times y squared certainly generates a square term from the first term. I get A1 squared. So B2 A1 squared. The rest of the terms, though, generate higher order products. So that's it. I'm done. So this is my C2. Okay? How about my cubic terms? So again, on the left-hand side, it's C3. On the right-hand side, now it's getting pretty obvious. I'm going to get a B1 times A3. And then from the square term, B2, I'm going to get this term times this term. And I get that twice. So I get 2 times A1, A2, and that gives me a cubic term. And finally, I get my y cubed term, which cubes the A1 term. So I get A1 cubed. And that's it. So I can circle these equations. And now, when I have a cascade, I can just apply these equations. Let me give you an example of where a cascade may be useful. Let's say I have a transistor, and let's say I know I out as a function of V in. Okay? And let's assume that this current flows into a nonlinear resistor, right? And I'm interested in V out. So V out is basically I out, so it's some nonlinear function of I out. If I have a Taylor series expansion of this and a Taylor series expansion of this, you can see that effectively this current gets multiplied by a nonlinear resistor, and it's basically a cascade. So let's say that this resistor is described by, so V out is, let's say, R1 I out plus R2 I out squared plus R3 I out cubed, and so on. And I out is some Gm times V in, let's say Gm1, Gm2 V in squared, Gm3 V in cubed, and so on. Okay? And you might think, well, that's kind of artificial. Why are you putting a nonlinear resistor here? Well, actually, the output impedance of this transistor is nonlinear. So if this transistor were loaded by, let's say, a current mirror, then this analysis would apply. Okay. Questions about this? Okay, another interesting question to ask is the IP2 point for a, let's say, an input IP2 point for a cascade. In other words, you go out there and you buy 2 amplifiers, and I know the IP2 of amplifier A, and I know the IP2 of amplifier B. I need to cascade them to get enough gain. I know the gain of amplifier A. I know the gain of amplifier B. Of course, the overall gain is GA times GB. But what's the overall IP2 point of this system? Well, it's very simple. I can actually use the result that I just derived for cascade. I know that the ratio of C2 over C1 for the cascade, if I go back, I calculate that C2 is B1 A2 plus B2 A1 squared, and C1, of course, is B1 A1. Okay? If I write this as, I can just write this as A2 over A1 plus B2 over B1 times A1. Okay? And remember that the input IP2 power is proportional to C2 over C1. Right? Actually, sorry, it's proportional to C1 over C2. So this equation is telling me that I can multiply this by the right factor so that this proportionality turns into equality. It's telling me that the input IP2 of the overall amplifier, 1 over the input IP2 of the overall amplifier, is 1 over the input IP2 of amplifier A plus A1 Well, A1 is just the gain of amplifier 1 divided by the input IP2 of amplifier B. Okay? Now, this is actually a very simple result because we can interpret these terms individually. Let's say that the second amplifier is linear, right? So this term is infinity and it goes away. That would tell me that the input IP2 of the overall amplifier is dominated by the input stage, right? Well, let's say this amplifier were perfect. Let's say this amplifier were completely linear. Then its input IP2 would be infinite, and the overall IP2 would just be the IP2 of the second amplifier, but input referred. Of course, I have to input refer it, right? Because the signal power is here. If I tell you that the input power, intercept power is 0 dBm here, and I have 10 dB of gain, then an input of minus 10 dBm will generate the IP2 point, right? So this is simply the input referred IP2 of amplifier B. And if you're in a situation where the second amplifier input referred dominates, right? Let's say that, let me give you an example. All right, before I give an example, any questions about this derivation? Crystal clear. Good. All right, so let's do an example. Let's say that I have an amplifier with a gain of 20 dB and an input IP2 of plus 0 dBm. Okay? And now let's say I pick a second amplifier and it has an input IP2 of only plus 10 dBm. Now that sounds pretty good, but if I input refer this, I have to take this gain into account. It becomes minus 10 dBm. So you can see without really doing much math that because the IP2 input referred of this guy is 10 times the IP2 of this point, this will dominate. So amp B will dominate distortion. Okay. Is that clear to everybody? If on the other hand this input IP2 point is close to this point, then I have to take, basically I use the law that they're in parallel. So the overall IP2 is worse than the IP2 of either one, right? So if they're both equal, let's take another example. Let's say I use the same first amplifier, but now I go out and buy a more expensive amplifier that has a 20 dBm input IP2. Now if I input refer that, that's 20 dB minus 20 dB, so it's 0 dBm. And it's equal to the input IP2 of amplifier A. So basically, my cascade formula says I take these in parallel, and so the overall input IP2 of the cascade is minus 3 dBm. Okay? Any questions? So all I'm doing is using this formula here. I'm taking them in parallel, right? And then taking the inverse. So it's like having two resistors in parallel, right? Their parallel resistance is half the overall resistance. So that's where the factor of 3 comes from. Okay? Okay, well, can we do the same thing for IP3? Why not? We derived the equation, so let's go and look at the equations for IP3. So if I look at C1 over C3 of the cascade, oh, going too far back. Here we go. So here's the cascade formula. So C3 has 3 terms in it. So if I plug in B1 over A1, Actually, I like to take C3 over C1. That's going to be B1 A3 B2 A1 A2 times 2 plus B3 A1 cubed divided by B1 over A1. Okay? And if I just write this out to 3 terms, this is going to be A3 over A1. That's good. That's 1 over the input IP3 of amplifier A. Plus, let me take this last term here. I have B3 over B1 A1 squared. Okay? That's also good because this is basically 1 over input IP2, IP3 of the second amplifier, input referred by A1 squared. Okay? Which actually, I just realized I made a mistake on the last example. We'll come back to that mistake. And then I have this messy term. I have B2 over B1 A2 times 2. Okay? Now, engineers are lazy. We don't like messy terms. We don't have a good name for this, so we just say, forget it. This is the second harmonic interaction term. Interaction term. We do have a name for it, but we still don't like it. It's basically the second harmonic of the first amplifier mixing with the fundamental of the first amplifier mixing with the second harmonic, producing intermodulation. And it's basically, it involves an interaction of the amplifiers. It makes things complicated. We don't like complexity, so let's get rid of it. So here, I can now write an equation. If I just multiply this equation by a constant 4/3, so I multiply here by 4/3, here by 4/3, and here by 4/3, I can write this as 1 over the input IP3 of the overall amplifier, the cascade, is equal to 1 over the input IP3 of amplifier A, that's this term, plus power gain of amplifier A, input IP3 of amplifier B. Okay? This is the power gain because it's the voltage gain squared. Okay? So now the formula for input IP3 looks nice and simple. It looks just like the case of the IP2 point. I input refer the IP3 of my second amplifier by the power gain, and then I take them in parallel. Okay? Now, you guys can hopefully see the error I made before. I think I made an error. So here, A1 is not the power gain, right? A1 is the voltage gain. So this should be GVA, the voltage gain of amplifier A. And so this is, in the example, this is the voltage gain. Well, if I give it in dB, it's automatically taken care of. Okay, so coming back to this input IP3, the similar exact calculation that we did for IP2 also applies to IP3. Usually you get into situations where the IP3 of one device will dominate. So for instance, if I have an LNA and a mixer, we haven't talked about mixers yet, but a very common combination is LNA driving a mixer. And you'll find out later on that mixers tend to be pretty nonlinear. It's pretty hard to design a very linear mixer. So this will have a pretty low input IP3. And if I input refer that, that's going to be even lower. So I may get into a situation very easily where if I don't pick my components right, the linearity of the whole system is dominated by the linearity of the mixer. Okay, let's give a practical example. Let's say I design an LNA and it has a minus 10 dBm input IP3. Okay, and let's say it has a gain of 20 dB, a power gain of 20 dB. And let's say I design a mixer which has even a worse input IP3 of minus 20 dBm. Okay? Now if I input refer that, let's call this B, this A, at the input, it's minus 20, so minus 40 dBm. So it's 10,000 times smaller than the IP3 of the input state. So clearly, the mixer will dominate the linearity. There's no need to even use that formula because one term is 10,000 times bigger than the other term. Okay. Questions, comments? Okay. Now, officially, we'll start this lecture. This is just material I put on the side that I forgot to talk about last lecture. So the topic for this lecture is the effect of feedback on distortion. And I'll probably just introduce the lecture. We won't get very far into it. There's only about 10 minutes left. Before we start a new topic, any questions? Comments about distortion and linearity? Yes?
How do we correct distortion, or we just have to live with it?
Okay, that's a great question because that's the topic of today's lecture. We'll find out that feedback tends to reduce distortion substantially. So if you have a system that has too much distortion, one thing you can do is apply feedback around it, and that will reduce the distortion. Okay. Any other questions? All right, so before we start the feedback discussion, I do have one example here in my notes that we can do. Let's do an example of a long channel MOSFET. Okay, so a long channel MOSFET, examples are good. It's fine to talk about math, but always it's good to do some real examples to understand what we're talking about. So just as before, I bias this up at some quiescent point. I apply a small signal input, and I observe the output voltage, which is really proportional to the drain current. So I have a quiescent drain current plus an output. Now something interesting that comes up right away is the concept of having a quiescent point. Remember we discussed that any kind of even order distortion, like second order, generates DC bias. So what we find is that technically the output bias point varies with the input amplitude. Okay? If I had just a simple system like this, I would find that IQ is a function of the input. So I couldn't just simply take it out of the equations like I usually do. Right? Remember, cosine squared is 1 plus cosine at twice the frequency. So that one term generates DC. So even order produces DC. Okay? Now what I'm going to assume is that somehow I have a biasing network that forces the DC value of this to be equal to IQ. Okay, and I'm not going to talk about the details of that biasing. Somehow there's either a feedback loop or some kind of system forcing the bias current to be IQ. So let's assume that that's the case. Let's just work with this and then we'll come back to that assumption. So if I assume a long channel